Okay, grade 12, this is our last lesson in redox chemistry, and we are going to be taking a look at how we can calculate the standard reduction potential, or the voltage produced when we combine a couple of different elements to make a voltaic cell. So the electric potential of any cell talks about its ability to produce electric voltage. And I'd like to say potential rather than current so that we keep this accurate. The electric potential of any cell is going to depend on the nature of the half shells. Are they pushing or pulling on the electrons? Will they work together or against each other? Let's take a look at how we can figure all this out. We've been talking about a copper zinc cell for a while, and we have, in our last lesson, drawn the diagram showing how we could make up a voltaic cell and the electron flow when we separated the zinc and the copper half cells. And what we did was we started by going to our electrode potential chart, which is on the first page of our workbooks, and looked up the voltages or the reduction potentials for each of those cells. Now remember, in our workbooks, everything is listed in the form of a reduction. So for example, the zinc half cell is listed as zinc plus 2 gains 2 electrons to form zinc metal. The copper cell is listed as copper plus 2, if it gets reduced, will gain 2 electrons to form copper metal. So any metal or substance can be reduced. It really depends on the nature of the cell beside it. So the reduction potential for the zinc we discovered was negative 0.76, and for the copper was positive 0.34. Now this is what happens when we measure it against the standard of hydrogen. Hydrogen is the standard that all these were measured off of, and then we measured how much pull these guys had against for attracting electrons to themselves as ions to become the reduced metallic form. So the numbers themselves are arbitrary. What we know then is if we compare these two numbers, then we would find that the one with the higher reduction potential is the one that is more likely to attract electrons to its ion to form its metallic form. The other element involved is more likely to push its electrons off of itself and become oxidized. Anytime we're given two different elements and we're asked to figure out the voltage, step one will be to go and find those species on your electropotential chart. Write down the reactions as you see them and the voltages, the electrode potentials for each half cell as you find it. So in this example, I've written down both the zinc and the copper as reductions as we see on our chart and the voltages we see. Now the bigger value wins, so the copper value is going to stay reduced, and that means the zinc value will be flipped. And so instead of being a reduction potential, it's going to become an oxidation potential. Instead of being reduced, it'll be oxidized. So I write the same equation exactly backwards, and I flip the sign on the reduction potential to make it an oxidation potential. At this point, electrons that are being taken by the copper are being given off by the zinc, and they cancel. We can add the two voltages together, the reduction plus the oxidation value. So if we always take our reduction value, the bigger the two, and add it to the oxidation value, which was the smaller value flipped, we get the total value for the cell. This is also quite often called the EMF, or electromotive force of the cell. They mean the same thing. In this case, positive 0.76 and positive 0.34 add up to a total voltage of 1.1 volts. Let's do one more example completely together, as you might find it in a sample problem. Suppose I want to make a cell that is going to be between aluminum, which we know forms an ion of aluminum plus 3, and copper, which I know can form many ions, but we're going to pick copper too. Let's let's go and do everything we've put together in the last two lessons. We're going to figure out my half reactions, the voltages. We're going to figure out the overall reaction and draw the cell and even write a cell notation. We're going to do everything we can possibly do with this. I'm going to start by going to my chart on page 1, my electropotential chart. And from that chart, I'm going to look up the two reactions that have these species. On the left-hand side, I see that we can find the aluminum reaction looking like this. Aluminum plus 3 gains 3 electrons to form aluminum metal, and the reduction potential for that reaction is negative 1.66 volts. We've already looked up the copper. We can find it near the top of the right-hand column. It says copper plus 2 ion gains 2 electrons to form copper metal. The reduction potential for this half reaction is positive 0.3 volts. Always our first step. Find our two half reactions and their voltages. Now remember, the one with the larger value wins. It gets to stay a reduction. That means that this species will no longer be reduced. It will instead be oxidized. So to be oxidized, I'm going to write it backwards. Aluminum metal is oxidized to form aluminum plus 3 ion, and that will release 3 electrons. This is now an oxidation potential, not a reduction potential. As an oxidation potential, it's going to be positive 1.66 volts. The total voltage for the cell will be the sum of the two, positive 0.34 and positive 1.66, is positive 2.00 volts. We'll get 2 volts potential out of this electrochemical cell. The overall reaction is the sum of these two. Now, before I can add them together, I'm going to have to make sure that my electrons can cancel. And clearly right now they cannot. 2 electrons won't cancel 3. So I'm going to have to find a common factor, and I'm going to make it 6. So to make our copper reaction into 6 electrons, I multiply everybody by 3. And to make my aluminum reaction into 6 electrons, I multiply everybody by 2, all the way through. Oops, sorry, 6. There we go. Now my electrons in cancel my electrons out. My overall equation would be 3 copper plus 2 ions react with 2 aluminum metals to produce 2 aluminum plus 3 ions and 3 copper metals. This is the overall reaction for the cell that produces 2 volts. We can now draw an electrochemical cell for this reaction. We know that to draw an electrochemical cell, I start by needing 2 beakers, which I connect with a salt bridge. So this is my simple little bridge made of salt. I know I'm going to need 2 metal electrodes, one for each of the metals in my reaction, and I'm going to connect those 2 pieces of metal with a wire. Okay, at this point, let's start labeling up the cells. It doesn't matter if I put things on the left or the right. I have my copper reaction listed first above. So in my copper reaction, I see I need copper ion and copper metal. Clearly, the metal itself is the copper metal. And in the solution that this will be in, I'm going to have to put copper plus 2 ions. And I could use copper chloride, copper sulfate, whichever source to be available. For the aluminum reaction, the strip of metal will be my aluminum metal, and in the solution, I'm going to need to have a source of my aluminum plus 3 ions. So I have my species there. There's a couple of more steps we have to do. We can see that aluminum was oxidized. Oxidation always happens at our anode. I can see that copper was reduced, and reduction always happens at my cathode. Which way do the electrons flow in the wire? Well, the electrons always flow from anode to cathode. So my electron flows through my wire goes from anode to cathode, in this case from right to left. So this is everything that I asked you to label about a cell diagram. What does the cell notation look like? Well, we always start with our oxidation. The oxidation was aluminum metal reacting to form aluminum plus 3 ion. We separate it with a double line that represents a Salz bridge that would separate the two half reactions. And we finish it with the reduction, which is copper plus 2 ions being reduced to copper metal. We don't need to worry about the balancing in my cell notation. So this is absolutely everything that we've learned to do in the second half of the reduction oxidation unit. There are several more questions you can practice in your textbook in Chapter 20, and also the last 2 pages of your workbook have more practice questions with reduction and oxidation potentials and calculating cell potentials and drawing cell diagrams.